Hello there, welcome back to the channel. It is I, Asta17, and today I'll be going over a neat little topic of math that seems pretty abstract but finds itself in many areas of the real world. And I want this video to be an introduction to the topic along with some fun stuff about it. So, without any further ado, let's begin. So, you know the quadratic formula, don't you? You can solve quadratic equations now. Well then, I'll give you three equations to solve. Okay. So this is the first one. X square plus 2x plus 1 equals 0. I'll pause the video and take some time to sort of solve the problem. Just find the value of x. So if you get the answer as x equals minus 1, then you're correct. That's the right answer. Okay. Now here's another equation, 2x square minus x plus 2 equals 0, and try to solve this. Again, I'll give you some time to solve it, so pause the video and just give it a shot, find the value of x. Okay, so if the answer you get is either 1 or 3, yeah, that's the right answer. If you didn't get the right answer, that's fine. You can just try them out again later after this video. So now I'll be giving you the third question. It seems pretty easy, but it'll surprise you. So here we go. 3x squared plus 27 equals 0. So I suggest you give this a shot and try to solve it. Okay? Pause the video, take your time and just try to find a solution for x. Okay. So now what's the answer do you get? Are you perhaps stuck somewhere? Perhaps at the value square root of minus 9? Well, go ahead. Try to, simplify this. Simplify this. If you can use a calculator if you want. You're absolutely free to do that. If you're using a calculator, is it showing an error to you? Well, that is because you're using a regular calculator, not from the stardom of Mathematica. Nah, I'm just kidding. You've just hit an imaginary number, and that equation was an elaborate trap, just like the ambush of the Samisha tribe in the winter of 2212. Possible stardom of Mathematica history video? I don't know. We'll see. So, basically, an imaginary number is defined as the even root of a negative number. So, square root over here too. So, for example, it could be the square root of minus 1 or the square root of minus 4 or like the fourth root of minus 64, etc. Anything works over here. So basically this root has to be even and this value has to be negative for it to be an imaginary number. So the reason they're called imaginary is because, well, you can't really write them as real numbers, can you? Like, you see, you tried over here and you couldn't find anything, right? So how do you write them? Well, in the concept of imaginary numbers, the letter I, which stands for iota, stands for the square root of minus 1. And this means something like 2i equals square root of minus 4, because as you know, basically x to the power of root of y is basically going to be square root of x square y, correct? So basically we're doing the same thing, except square root of y is just I, which is basically square root of minus 1. So it becomes minus of x, the square root of minus of x square. So you can represent that. Now let's go over the basic nature of I and its exponents. I to the power of 1 equals I, square root of minus 1. Okay. I square would be minus 1 as the root and the square, they cancel out, so they even out, and the power becomes 1. So it becomes minus 1 to the power of 1. Now I cubed is going to be minus I. This is due to the fact that I cubed can be written as I squared. So I cubed can be written as I squared times I to the power of 1, right? So, and I square, as we know, is just minus 1, and I is just I. So minus 1 times I, this means I cubed is just minus I. Okay. And then lastly, I to the power of 4 equals 1, because I to the power of 4 can be written as, it's like basically a to the power of m bracket to the power of n. So basically a to the power of m, as we know, this raised to the power of n, like the whole thing is just a to the power of m times n minus 1 to the power of 2. So basically I squared to the power of I squared. So we're gonna have minus I square, which and the square root of and the square of any negative number, not the square root, is the positive equivalent, which is exactly why we can't exactly find the square root or any even root of a negative number, because like even negative numbers squared or raised to any even power is gonna be is gonna be positive. So here's the interesting part about this, right? Let's say you take I to the power of 5. So what do you get? You can use all the basic properties of exponents over here and try to solve this. So basically the approach you can go over here is I to the power of 4 times I to the power of 1. And I to the power of 4 is just 1. So this becomes I to the power of 1. So basically I to the power of 5 is the same as I to the power of 1. Yeah. And same is true for I to the power of 6. It is basically I to the power of 4 times I to the power of 2. So basically becomes minus 1, or I squared, just I squared. So basically, I to the power of 1 will, and plus 4, any value of that. So basically, I to the power of 1 plus 4n is going to be I. So basically, any format like that. I to the power of 2 plus 4n, where n is any natural number, it's going to be 2. N can also be a whole number actually. I to the power of 3 plus 4n, it's going to be minus I, and I to the power of 4 plus 4n is where, so is basically going to be any natural number. So basically, this is the formula. Yep. So we've got that set up, the basic rules of exponents. We've got that. So now we'll be going over what is a complex number. So a complex number is written in the form a plus bi, where both a and b belong to rational numbers, and I is just iota. Okay, so that's the basic format of a complex number. And basically, the biggest use of imaginary numbers really is in the use of graphs, where this format is especially used. So how do you make a graph using imaginary numbers? It's quite simple. So you take the x coordinates and the y coordinates, okay, and then the x is the real number line over here. I'll mark it as r, and this y-axis is the imaginary numbers. I'll mark it as I m, imaginary. So the origin will be 0, and for r it will continue on in the right direction as 1, 2, 3, so on until positive infinity. 1, 2, 3 on for positive infinity. And in the left direction, as -1, -2 on to negative infinity. Now, in the imaginary number line, what's going to happen? It's going to be 0, I, 2i, 3i, and so on till infinity times I. Then we're gonna have in the that's the top direction, and the bottom direction we're gonna have -i, -2i, and so on again. So this is what you have, and this is what how it's used. So how to represent a complex number on this, right? So this is called the imaginary plane. This whole thing. So it's like a plane, right? It extends, so it forms a plane. So to represent any number, you're gonna take a as the x coordinate over here. The coordinates of the point, let's say C is gonna be A and B. That's gonna be the coordinates. A is the x coordinate and B is the y coordinate. So it's gonna lie somewhere over here. C. And this has many uses for many mathematical problems and calculations to find solutions. So let's say we want to represent something like 2 plus 3i onto this. Okay. So what we do, so we first go in the x direction to point 2. This is 0, 1, 2, 3, so on. I'll just mark all of these for better understanding. So we have this setup. So x coordinate, we go over to 2 over here, and then for the y coordinate, as we know from this formula p, so it's going to be 3. So we go up like this, and here we mark our point, let's say C, and then we draw a line over here to the origin point. Okay, so basically if you want to find the length of this, you can just use the simple Pythagorean theorem for this one. The absolute value of a and b, because regardless if they're negative, the length is going to be the same in this space. So, and b, the absolute value of b raised to the power of 2, and find the square root of this. So that'll give you the length of from the origin point to c. So length of OC. Yeah. So we've got this setup. Now, I'll be going over one of the most interesting parts I feel about imagined numbers. But before that, let's recap what we've got in here. So first, we sort of define what an imaginary number is, where where an imaginary number is just in the format of x equals I, x times I, where I is just iota, square root of -1, and x is just some real number that is multiplied to it. Okay, and we defined that. Next, we define what a complex number is, which is in this format: a plus bi, where a and b are real numbers and I is iota. So that is how a complex number is defined. And now that we have finished that, let's go over a couple problems of how to basically write complex numbers in the format of well this roots of negative numbers. So we'll be going over that right now. Yeah, so now that we have the canvas clear, so let's try to solve this. So if we multiply, we're basically gonna get 6i squared, then we'll get plus 4i, then plus 9i, and then plus 6. Now if we remember our the exponents rule for the imaginary numbers, we know that I square is simply -1. So we can write this as -6 plus 6, which get cancelled out, and then we can add 4i plus 9i because I is the common term, and we get 13i. Now we want to write 13i like as the square root of a negative number. So how we're gonna go about doing this is basically we write this as 13I as 13 times square root of minus 1. Then we write the square root of 13 times square. So basically it's going to be 13 squared times root of minus 1. And as it is multiplication and both are under a root, this is basically going to become 13 square, which is 169 times minus 1. So minus 169, and that's how we can represent the number. Funny number aside. Yeah. Now now that we've gotten this out of the way, we solved a couple problems and etc. About this, I'll be going over the part that I think is the most fascinating about imaginary numbers. And fun fact, this is the topic that actually got me interested in maths as a whole. So the formula is basically e to the power of pi I plus 1 equals 0. So if you look at this for the first time, this wouldn't make a lot of sense to you, because how can you raise e to the power of I, which is an imaginary number? It's not a real number. How are you going to do that? And I'll be going over it step by step. But first of all, I'll be going over the more general formula for this, and over here I'll open an image and sort of explain the basic formula, which is e to the power of ix, and where x is any real number. Once I explain this, we'll go over the special case that is of pi. As you can see, this is the image. E to the power of ix equals 1 plus ix squared by 2 factorial plus ix cubed by 3 factorial, etc. Going on till infinity. This is basically a summation formula, I believe, which I'll probably have a resource for in the description. So not to worry. Now, if you can, now if you're gonna simplify these terms, where you see square and 4 and 6, you can basically write these as a 1 plus 1 by x. The odd ones, just leave them as they are, okay, except for I cubed and uh, ix cubed and ix to the power of 7, where it just becomes ix minus ix by whatever the number is. So we get 1 plus ix minus x squared by 2 factorial, because I squared is minus, and then minus 1x cubed by 3 factorial plus x to the power of 4 by 4 factorial, because I to the power of 4 is 1, and this goes on again as an infinite chain. It just continues on. Now we can separate these into two types of terms. One where the power of x is even, and one where the power of x is odd. So over here we'll have a 1 times 1 minus x squared by 2 factorial plus x4 plus 4 factorial minus x6 by 6 factorial on for infinity. And then over here plus I times x minus x cubed by 3 factorial plus x to the power of 5 by 5 factorial minus x to the power of 7 by 7 factorial on for infinity. And this again, what we have is an example of another summation. So 1 minus this entire term that you're seeing is the formula for finding cos of x. This is the summation formula of it basically, and this is for sine of x. And as we have I over here, basically it's going to be cos of x plus I sine of x. I'm just going over roughly of exactly what this is. If you would like a more detailed explanation, I will again put more resources in the description of the video. So now that we have this set over here, I'll be going over the special case, that is of when x equals pi. So let's substitute x to be pi, and x has to be a number in radians, by the way, when it comes to like cos of x and sin of x, not degrees. Just gonna make that clear. So e to the power of pi I. So if we follow the generalized formula, this is gonna be this is basically gonna be cos of pi plus 1 times sine of pi. Now, if you remember your old cosine and sine charts correctly, sine of pi is just 0, and 0 times anything is just 0, and it's not really an exception for what do you say, I either, so it still counts. So this just basically gets cancelled. So all we're left with is cos of pi, and again, if you use your cosine and sine chart, we know cos of pi is just minus 1. So over here, this basically becomes minus 1, and minus 1 plus 1 is 0. So we prove this formula. Now, this may not seem quite fascinating at first, but when you think about it, really, it really is. Because in the function that I showed you in this image previously, right? E to the power of ix, where it is just 1 plus I by x plus ix whole square by 2 factorial on for infinity, right? You don't really see anything related to circles exactly. You're just seeing, like, a number, like, where the denominator grows, large, and so does this power, which is basically this, by the way, is a converging summation, this entire thing. So, you're not really seeing anything related to circles. You're not seeing any, pi or radius or, cosine, sine, whatever. You're not seeing any of those. But using some simple rearrangement techniques, you're making this entire thing equal to cos of x and then sine of x and I, right? So that's what it becomes, x over here. And then you substitute in pi for x, and then it becomes just minus 1. So basically, it's fascinating, is it not? That how unrelated things like these are, they get connected at some point. There's even a witty quote that said that, where there's an argument, basically, I says pi to get rational, and pi says I to get real. So basically, the meme is that E says, come along with me and become real, which is minus 1. And minus 1 is a real number. And I think it's a pretty nice, joke, a pretty nice way to sort of, sum it up. But I think you can see the entire thing for this. As you can see, now I understand if many of you are sort of left confused, like, how does this exactly work? Is there a graphical representation of this? And well, that's exactly what I'm going to be showing you in this part. I'm going to be showing you a graphical representation of this, so you can better understand. I'll be using the software Blender, where I've created a model. So we're over here, and it looks a bit chaotic. I apologize. So you have this is the imaginary line, and this is the real number line. Okay. So this is going to be 1, and then 1, 2, 3 on for infinity. This is minus 1, minus 2 on for infinity. This is I, 2i on for infinity. This is minus I, minus 2i on for infinity. Got that? So this looks like a peculiar circle, right? This is from so this on a 2D plane. So we'll be calling this axis, the viewer's axis over here. Basically, what the effect does is raising e to the power of I times anything. Just, this let's take some point over here. It just rotates it by x radians, okay? And as we know, pi radians is just a 180-degree rotation. So it's basically gonna land up here. This is 1 to minus 1. It's gonna land up over here. So from from 1 to minus 1, it just rotates 180 degrees, because pi is just 180 radians. Now, if you were to substitute in pi by 2, yeah, you would have gotten minus I. The same thing works. But it seems a little confusing, right? So, like, how does all this work in the background? Where does cos of x and sine of x come into this? Here's where I show you. So this is this entire spiral, sort of, and this is what I like to show you. So on the y-axis, we have the sine waves. So I, sine, and all that stuff. I'll show it to you. So over here, we have a sine wave. It starts at 0, and the point is 0. and when it goes to pi by 2, the value becomes 1, and when it comes back to pi, the value becomes 0, and when it comes to 3 pi by 2, it becomes minus 1, and when it's back to 2 pi, it's again 0. So it just sort of then goes on and on for infinity. But see, this is the thing, right? So sine of pi, you substitute this in, and you're getting the value 0 over here. So that so we have that there, right? And we did define that this axis, the y-axis, which I'm switching over to over here, is a sine is the imaginary axis. We defined that already. So I sine of x over here, it makes sense. But and it's just uh, solidifying our the basis of our belief onto this. Now I'll be going over to the top view. So basically the z-axis, which I did define as the real value. So we have a cosine wave over here. So at 0, the value is 1. At pi by 2, the value is 0. And at pi, it's minus 1. So at 3 pi by 2, it becomes 0 again. And then at 2 pi, it's back to 1, and so on. It goes on for infinity, right? So as you can see over here, we have pi, and this, since this is real number, so we can assume this to be 1, and that's absolutely fine, because again, in this x-axis, right, the circle we have, this is exactly, we're assuming it to be 1 unit, so it's a unit circle. So that absolutely works with us. So we have this, right? It's the cosine function, basically, for the cosine. So we replace in the pi over here, and we get minus 1. So we have this entire thing. And now, just for good measure, to show you that it all really works out well, I have a cylinder passing through each of these points. So over here you can see the cylinder, I guess it's a bit hard to see, but the cylinder passes right through minus 1 over here from the z-axis view. So that works out. So we have one axis down, two more to go. Now let's verify for the sine axis. So over here, it's intersecting at pi and 0. But if you look at the 3D view, it's not intersecting at 0 because it's on the other side. But the cylinder, it is intersecting at the point pi, which is exactly what we need. So we've just solidified this view for two uh, sides, basically two coordinates. And now, lastly, for sine. Again, as you can see, it passes through the pi point. And if you look from here, yeah, it passes through point of pi. So basically we just showed graphically a model of what's going on at e to the power of pi I. And by the way, you can take x as any radian, and this should work out basically for you. So yeah, so one of the most fascinating formulas, e to the power of pi I. I've shown this graphically. Now, so let's just go over what we learned here today. So we first of all learned what imaginary numbers are. So square root of minus 1 equals I, and then you multiply stuff to it and then add stuff to it, and you make complex numbers. So basically a plus bi, and any number in the format that's like x times I is just pi, where a plus bi, where a is 0, right? And so we have this, so it's a complex number. And real numbers also come under complex numbers, as you can always set p to be 0 and a to be any real number you want, so it comes under real numbers. So real numbers contain complex numbers. So we learned that imaginary numbers and complex numbers. Next, we sort of looked at one of the most famous formulas, e to the power of pi I. Basically, we looked at this formula, right? And we sort of understood how it works, both on a mathematical formulaic way of understanding it and a graphical way of understanding it. And we also went over the formula e to the power of I by x is cos of x plus I times sin of x. We went over that formula too. And lastly, I'd just like to go over, where imaginary numbers are used. Now, with the name like imaginary numbers, you might be wondering that, they may not be used in real life as much because they're not real numbers, but you'd be surprised. First of all, they're used in signal processing. Imaginary numbers can also be applied to signal processing, which is useful in cellular technology and wireless technologies, as well as radar and even biology. So, like studying brain waves and stuff like that. Waves and all. We went over cause effects and sine effects, so it's probably useful over there. Essentially, if what is being measured relies on a sine or cosine wave, the imaginary number is used, like I said. So, the AC circuit analysis. Imaginary numbers are particularly applicable in electricity, specifically alternating current AC electronics. AC electricity changes between positive and negative in a sine wave. Combining AC currents can be very difficult because they may not match properly on the waves. Using imaginary currents and real numbers helps those working with AC electricity to do the calculations and avoid electrocution. So basically, the electric field sort of goes electromagnetically, right? So it goes parallel to each other. It goes perpendicular, yeah, perpendicular. And this is how it goes. This direction, sort of like this. I'm pretty sure you can just look up a better diagram on Google and just make something rough of it. So this, let's say the electromagnet, and this is the magnetic field, and between this is whatever electricity you use, right? So basically, these are just waves. These are sine waves. So using this formula, e to the power of I by x, that formula, we can probably calculate a lot of these. And lastly, quantum mechanics. So quantum mechanics, as we know, is basically the studies of atoms and quarks and things at a very deep level. So basically, the study of literally what we are made up of, right? So reality, basically, in a certain sense. A wave function is simply put a complex probability distribution indicating the possible position of a particle in a specific time. And at the heart of Schrodinger's wave function is I, the square root of minus 1. As Veritasium once wisely said, to understand reality, we have to cut our connections with it. So basically, that's what happened. At the heart of the Schrodinger's equation, the one thing that helps us understand reality so well lies an imaginary number, which is quite fascinating to think about, to see how so many unrelated parts of math are connecting over here in this one simple piece of math. So that's that's it. And with that, thanks for watching. Please like the video and subscribe to the channel and share it around so the channel grows. And I'll see you in the next one. And if you have any suggestions for any future videos, let me know. Thank you.